Next, let us see about strong and weak electrolytes and ionic equilibrium. On the basis of conduction of electricity through solutions, Faraday classified substances into two types. One is called electrolytes and the second one is called non-electrolytes. So, let us see what are electrolytes. Electrolytes. Electrolyte is defined as a compound whose aqueous solution or melt conducts electricity. So, electrolytes, they conduct electricity in aqueous solution or melt. Melt means molten state. So, substances which conduct electricity in aqueous or molten state, they are called electrolytes. An example for electrolyte is aqueous solution of inorganic salts, acids and bases. Now, what do you mean by a non-electrolyte? Non-electrolytes means they are substances which do not conduct electricity. They are called in aqueous solution or molten state. They are called non-electrolytes. For example, aqueous solution of sugar, urea, all these are examples for non-electrolytes. So, we are going to study or we are going to discuss about the electrolytes. Electrolytes means they conduct electricity in aqueous or molten state. Now, in electrolytes, the conductance is due to the presence of ions. So, we are going to study about electrolytes. The conductance, or they conduct electricity with the help of ions. So, ions are responsible for the conduction of electricity. And these ions are produced by the dissociation of substance. That means when you add electrolytes to water, it dissociates into ions and these ions conduct electricity. And different electrolytes dissociate to different extent. And depending upon the degree of dissociation, Faraday again classified electrolytes into two types, strong electrolyte and weak electrolyte. So, next is the strong electrolyte and weak electrolyte. So, these electrolytes are again classified as strong and weak electrolytes. So, let's see what are strong electrolytes first. And the strong and weak electrolyte classification is based on the degree of dissociation of the electrolyte. Now, what do you mean by strong electrolyte? Strong electrolyte means electrolytes which dissociate completely into ions in aqueous solution and they are good conductors of electricity. So, strong electrolytes means they dissociate completely into ions in aqueous solution. So, here more ions are produced means they are very good conductors of electricity. And example, sodium chloride, potassium chloride, sodium hydroxide, all these are examples for strong electrolyte. So, when you add sodium chloride to water, aqueous medium, sodium chloride will dissociate into which all ions? Na plus Cl minus ions. Same way, if you add sodium hydroxide, then sodium hydroxide dissociates into Na plus OH minus ions. Now here the dissociation or ionization. Now both the terms means the same. So I will use both the terms dissociation or ionization. Both means the dissociation of electrolytes into ions, or we can use the term ionization also. Now here this ionization, since it's completely dissociated into ions, we put only a single arrow. Okay, this is not a reversible reaction. This is a complete dissociation, so we will give only a single arrow. So this is about strong electrolytes. So what are strong electrolytes? Electrolytes which dissociate completely into ions in aqueous solution. They are strong electrolytes and they are very good conductors of electricity. Now next, let's see about weak electrolytes. So the second classification is weak electrolytes. Now, what are weak electrolytes? Weak electrolytes dissociate to a small extent in aqueous solution and they conduct electricity to a small extent. So, means weak electrolytes, they are partially dissociated or partially ionized in aqueous solution. So, what do you mean by weak electrolyte? They dissociate partially in aqueous solution. And example for weak electrolyte is acetic acid. This is a weak acid. Now for a weak base, example is ammonium hydroxide. So this acetic acid and ammonium hydroxide, they are weak electrolytes, and acetic acid is a weak acid, weak electrolyte which is an acid, and ammonium hydroxide is a weak electrolyte which is a base. Now let's see the decomposition of acetic acid. It's a weak electrolyte. So how can we write the decomposition? CH3COOH, and here it's a reversible reaction, or this reaction is at equilibrium. Now acetic acid dissociates and we know it's partially dissociated, which means CH3COOH dissociate into which all ions? We get CH3COO minus plus H plus ions. Now this is a partial dissociation or partial ionization, means there is some undissociated acetic acid molecules also. Undissociated acetic acid molecules present. So if you look at acetic acid solution, means that solution will contain which all things? It contains acetate ion, H plus ion and undissociated acetic acid molecule. So these three are present in the acetic acid solution. Okay, and this is at equilibrium. Now equilibrium, why is it at equilibrium? Because there is undissociated acetic acid molecule and ions. So the equilibrium is between the ions and the undissociated acetic acid molecule. Okay, so weak electrolytes, we have the equilibrium reaction, or equilibrium is established only in case of weak electrolyte. Now in general I am going to write the ionization of a weak electrolyte. Ionization of a weak electrolyte, AB, is written as AB plus aqueous will give A plus aqueous plus B minus aqueous. Now this type of equilibrium is called ionic equilibrium, means equilibrium involving ions, and ionic equilibrium is between the ions and undissociated electrolyte. Okay, so this is ionic equilibrium. In ionic equilibrium, the equilibrium is between the ions A plus B minus and the undissociated electrolyte, that is AB, because this is a weak electrolyte which is partially ionized in solution. Now I am going to apply the law of chemical equilibrium to this expression, to this reaction. So how will we write the expression for equilibrium constant? Kc is equal to concentration of A plus into concentration of B minus divided by concentration of AB. Now we know that this AB is a solid, and we know for pure solids concentration of AB is taken as 1. So that concentration of AB, it's a constant, into Kc will give rise to a new constant which is denoted by Ki. So Ki will be concentration of A plus into concentration of B minus, and Ki is called ionization constant. It is called the ionization constant. Okay, so this is possible only in case of weak electrolytes. That is an expression for ionization constant. Now next, let us see an expression to find the ionization constant of a weak electrolyte. So next heading is ionization constant of a weak acid. Here the electrolyte taken is acid. So the ionization constant is denoted by Ki. Now since the electrolyte taken is acid, it is denoted by Ka. Or instead of ionization constant, you can also say dissociation constant of a weak acid, denoted by Ka. Now this is a derivation, so this can be asked as a question. Derive an expression for the ionization constant of a weak acid, or derive an expression for the dissociation constant of a weak acid. So we are going to start the derivation taking acetic acid as example. So we know acetic acid is a weak acid and it's partially ionized in aqueous solution. So I am going to write the equation of acetic acid, aqueous plus H2O liquid in equilibrium gives CH3COO minus aqueous plus H3O plus aqueous. H3O plus is called hydronium ion. Now this H2O will accept H plus from CH3COOH and we get H3O plus, which is called the hydronium ion. Now I am going to write the expression for equilibrium constant, that is Kc. How will we write the expression? Molar concentration of CH3COO minus into molar concentration of H3O plus divided by molar concentration of CH3COOH into molar concentration of H2O. Now, this molar concentration of H2O is a constant because in dilute solution concentration of H2O remains the same, so it's a constant. So the product of Kc and the constant is denoted as, or it is equal to Ka. We are taking another constant denoted by Ka. So again I am going to rewrite this expression, that is Kc is equal to CH3COOH. This expression as, instead of Kc I am going to write the new constant, that is Ka is equal to molar concentration of CH3COO minus into molar concentration of H3O plus divided by molar concentration of CH3COOH. So this is the expression for the ionization constant of a weak acid, which is denoted by Ka. Now Ka is called the ionization constant or dissociation constant of a weak acid. And this Ka, it's a dimensionless quantity. Okay, so there is no unit for the acid dissociation constant or ionization constant of weak acid. Now, same way we can have an ionization constant for a weak base. So, let's see next. Ionization constant or dissociation constant for a weak base. It's a weak electrolyte. Here the electrolyte taken is a weak base and here it is denoted by Kb. Ka represents the ionization constant of a weak acid. Kb represents the ionization constant of a weak base. Now let's see the example. Let's take the general equation. Base MOH, aqueous solution dissociates to give M plus aqueous plus OH minus aqueous. Now here also you can write the expression as Kb. What will be the expression? Molar concentration of M plus into molar concentration of OH minus divided by molar concentration of MOH. So this is the expression for the ionization constant for a weak base. Okay, and again Kb also is a dimensionless quantity. Now this is the expression to find the ionization constant, or if you are asked to find the ionization constant of acetic acid, you can derive the expression like this. Ka is equal to concentration of acetate ion into concentration of H3O plus divided by molar concentration of CH3COO minus. Now next we are going to see an expression for degree of ionization or degree of dissociation. So next is expression for degree of ionization or degree of dissociation. And degree of ionization or degree of dissociation is denoted by alpha. And here also this is for weak electrolyte, and we are going to see for weak acids. So degree of ionization, we are going to find an expression for alpha for a weak acid. So again, how will you define this alpha? Alpha denotes the degree of ionization, means the extent to which that electrolyte has ionized. So how can we define alpha? Alpha is the fraction of total number of moles of electrolyte ionized. That is the definition of alpha. Total number of moles of electrolyte ionized. Now let's see the derivation for alpha, to get an expression for alpha. For this, consider a weak acid. Again we are going to take acetic acid, and let capital C represents the initial concentration of acid in mole per liter. C is the initial concentration. And alpha represents the degree of ionization. So I am going to write the expression CH3COOH plus H2O gives CH3COO minus plus H3O plus. Now all this in aqueous state. Now we know that at time t is equal to 0, we have only acetic acid, means the reaction has not started. So at time t, initially we have only acetic acid with us, whose concentration is C mole per liter, because we have taken the initial concentration of the acid as C, capital C. And here the reaction has not taken, so the concentration of the product formed is 0. Now what happens as the reaction proceeds? Acetic acid will dissociate into acetate ion and H plus ion. Okay, it's not complete dissociation. So from C, which was the initial concentration, C alpha got dissociated. So as time goes, or at time t, here the CH3COH concentration will be C minus C alpha, because from C mole per liter, C alpha got dissociated. So when C alpha gets dissociated, what is the number of or concentration of acetate ion and H3O plus ion produced? That will also be equal to C alpha, C alpha. So C alpha represents the equilibrium concentration of ions, and C minus C alpha equilibrium concentration represents the equilibrium concentration of undissociated acetic acid. Okay, now I am going to write the expression for Ka, that is the dissociation constant of weak acid. Ka, we already wrote it. What is the expression? CH3CO minus into concentration of H3O plus divided by concentration of CH3COOH. Now substituting the equilibrium concentration at time t, we have Ka is equal to concentration of CH3CO minus is C alpha into C alpha divided by C minus C alpha, or you can write Ka is equal to C square alpha square divided by C into 1 minus alpha, or we get the expression as C alpha square divided by 1 minus alpha. Now this 1 minus alpha in the case of weak electrolyte, the value of alpha is very small and can be neglected in comparison to 1. So 1 minus alpha can be taken as equal to 1 because it's a weak electrolyte. So that alpha or degree of dissociation is very less. So that alpha can be neglected in comparison with 1. So we can take 1 minus alpha is equal to 1, or we can write the final expression for Ka as Ka is equal to C alpha square, or we can write alpha, degree of ionization alpha will be equal to square root of Ka by C. So this is the expression to find the degree of ionization of a weak acid or degree of dissociation of a weak acid. That is alpha is equal to square root of Ka by C, where C is the molar concentration or concentration in mole per liter, which means our molarity, that is C, and Ka is the acid dissociation constant or ionization constant of an acid. And if you want to find Ka, if alpha is given, you can use Ka is equal to C alpha square. So both these expressions are important. Now if it's a weak base, what will be the expression for Kb? Weak base, for weak base we have Kb is equal to C alpha square. So what will be the degree of ionization alpha for a weak base? Square root of Kb by C. Okay, so these two expressions are for weak bases, that is to find the dissociation constant of a weak base and degree of ionization of a weak base. So with this we complete about the strong and weak electrolytes, and about weak electrolytes we discussed about the dissociation constant for a weak acid and a weak base, and also we got an expression to find the degree of ionization or degree of dissociation of a weak acid and a weak base. Thank you.